All right, hi calculus, how are you? In this screencast, we're going to pose the inevitable question, which is when we're looking at a definite integral, and we know that a definite integral describes exact net signed area. You'll notice what I wrote here. In this case, given this function and the shaded area, I actually wrote that the net signed area in this case describes the exact area. I took out the word net, even though I could have included it, because here the exact area happens to be equal to the exact net signed area. And the reason why is because the interval of definite integration is from 1 to 2, right, heading right, and the function's above the x-axis. So in this case, in some cases, the definite integral, which always describes net signed area, sometimes the net signed area happens to equal the exact area, and that is the case here. Okay, so we know this to be true. Here is the function, lower limit of integration 1, upper limit is 2, okay? And what I'm going to talk about now is the lead up to the inevitable question, which is what happens if you have an area like this shape here, where we can't just use simple geometry to find that area, okay? And this is a pretty big deal. We're going to start with this idea. This exact area that right now, when you look at this exact net signed area, which describes the exact area, we cannot find that exactly yet. So this screencast is about approximating a definite integral using what's called a Riemann sum. And in particular, we're going to start with a finite Riemann sum, okay? So the obvious question that you will have here is, what is a Riemann sum? Well, let's develop it, okay? Let's develop it with these ideas here. So I'm going to go to this area right here. And what I'm going to do is I am going to divide up this shaded region into rectangular intervals. Okay, and let's say that I want to have 4 rectangular intervals, and I want their widths to be the same. Okay, and I don't think it's going to take too much effort here to see that. Oh dear, hold on, let me fix that. Okay. So I want to have 4, these are called 4 sub-intervals, right? If the entire interval of integration is from 1 to 2, I've just created 4 sub-intervals, all right? And it may not look it exactly because I'm not a perfect artist, but I want these demarcations to be exact in length. So here I'm going to say n equals 4, which in this case is the number of rectangular subintervals. And what I want to do here is call this here, okay, and you may find yourself needing to be really clear in your notes here, okay? I'm going to say, let's call this, right, the changes in x, which are supposed to be the same, okay? This change in x, I'm calling it change in x. So each rectangle has a width of delta x. When I talk about making the height of the rectangle, follow my pen here. I could choose to make the height of the rectangle. I can take the left endpoint and do a rectangle this way, right? And then so in fact, let's just do that, right? Let's take the left, I can make rectangles like this, right? Now, why did I say the word left? Well, because I'm saying here that the area of these 4 rectangles, if I used the left endpoint of each interval, in other words, look at interval 1 right here. This is the left endpoint of the first interval, and I figured out the height of the rectangle by using the function value at the left endpoint. The second rectangle, I go to the second interval, here is the second left endpoint. F of the second left endpoint gives me the height of this rectangle, so on and so forth, okay? clearly you can see that the area of these four rectangles in this case would be an under approximation of the actual definite integral. Because I could pick the left endpoint, obviously you see that I just made an arbitrary choice. I just chose the left endpoint to use to decide on, okay, I just fell off my words. I just chose the left endpoint as the choice of the height of the rectangle. Because it is often easier to just learn the math of the right endpoint first, what we're going to do, everyone, is do a right endpoint rectangular approximation. If I take the right endpoint of each rectangle, you will see that we get this. Okay? Right endpoint. What that means is in each subinterval, I am taking the right endpoint of each subinterval using the function evaluated at that right endpoint to get the height of each rectangle. Now, just for clarity, I am going to go over and make sure we see where all the demarcations are. Okay? I'm just going to do this just to make it clear. All right, now here's what I'm going to do. I'm now going to go over here and do this. Well, I chose 4 rectangles, and delta x is the width of each rectangle, and delta x is constant through each subinterval. So really, I could say delta x just equals the entire interval of integration, 2 minus 1, divided by the number of rectangles I chose, which was 4. That means delta x just equals 1/2. And I know you probably could have figured that out on your own, okay, just by eyeballing it. Now, the first, follow me here, the first right endpoint, right? Tell me if I'm right or wrong. The first right endpoint is the beginning of the interval of integration plus 1 delta x, right? So in other words, this first right endpoint right here, does that equal 1 plus 1 delta x? Yes. Does the second right endpoint equal 1 plus 2 delta x's? Yes. Does the third right endpoint equal 1 plus 3 delta x's? Yes. And finally, the fourth right endpoint equals 1 plus 3 delta x's. So if we know that the first right endpoint equals 1 plus 1 delta x, and remember, mind you, this choice of 1, I mean, I could have chosen my interval of integration to be 0, right? So this 1 will not always be 1, obviously. The second right endpoint will be 1 plus 2 delta x's. What I'm getting to here is the kth right endpoint. The kth right endpoint would equal 1 plus k delta x. Okay? Now, what would be the height of the kth rectangle? Well, the height of the kth rectangle is determined by, look over here, the function value evaluated at the kth right endpoint. So don't forget, underlying all this was f of x, right? F of x was down here. And what we did was we evaluated, okay, we evaluated the function f of the kth right endpoint. So the height of the kth rectangle is f of 1 plus k delta x. And now I'm moving to the kind of finale here. The area of the kth rectangle, well, area of a rectangle is just length times the width. So the area of the kth rectangle is, there's the width, delta x, times f of 1 plus k delta x. Now here, since we know what f of x is, see that? X squared plus 1. In this case, this equals delta x plus 1 plus k delta x squared plus 1. Okay, now I'd love to have the area of my kth rectangle written without delta x here. Well, I know that delta x is, in general, right here, look over here, it's 1/2, right? So I'm going to put this 1/2 in for delta x and delta x. And what I get when everything is cleaned up and completely contextualized, I have this. This is the area of the kth rectangle. Now, in this picture here, what I've done is I have approximated the definite integral using the area of how many rectangles? 4. And I just arbitrarily chose that. So now, the number 4 that is. So now I want to get an expression for the sum of all 4 rectangles areas. And this is going to equal our old friend, the summation, okay? The summation from k equals 1, there's 1 rectangle, up to 4. And what the summand is going to be, the summand is this whole thing right here. That is the summand. So the summation from k equals 1 to 4 of 1/2 plus 1 plus k over 2 plus 1, squared, plus 1. And what we have, ladies and gentlemen, this right here does what you're saying. This is telling someone to add up from k equals 1 to k equals 4. This summand. And when you plug in k equals 1, into the summand, that will equal the area of the first triangle. When you plug in k equals 2 into this summand, it will equal the area of the second triangle, and so on and so forth. When you add up all those 4 terms, the sum of those 4 terms will equal the area of these 4 rectangles. And what I'm going to say here is this. This is very important. If I can do one line here, I would. But it's very important to note that this is, look what I'm going to write here. It's an approximation of the definite integral from, what's my limits of integration? There we go. From 1 to 2 of the function x squared plus 1 dx. And I could ask you more questions here. I mean, we know it's an approximation. We also know it would be an over approximation because I chose a right endpoint approximation and because the curve is concave up, right? You probably can see down the shadows there. Had I chosen the left endpoint approximation, I would have gotten an under approximation. This approximation here is an over approximation. So now to answer the question, what exactly is a Riemann sum? This right here is a Riemann sum. This is a finite, right? A finite. Why finite, everyone? Finite because I'm just adding up 4 terms, because the upper limit of summation is not infinity. This is a finite right endpoint Riemann sum. So what is a Riemann sum? Well, a Riemann sum is an approximation of a definite integral when the upper limit of summation is a finite number. Why the word right endpoint? Because you're specifying in a Riemann sum which endpoint I used to approximate the height of the rectangle. A couple of things, everyone. Okay, remember what I said before. The fact that I started here at 1, right? This 1 here, right, was what gave you 1 here, correct? But it won't always start at 1, all right? And also, this 1 has nothing to do with this one here. This one just means like the first rectangle. All right, so now you know what a finite right endpoint Riemann sum is. Let's go to the second one that we're going to do together here. Here we have a function. Function is e to the x. And notice the interval of definite integration. So, and again here, true or false. If I write the definite integral as the definite integral from -2 to 5 of e to the x dx, right? This always equals net signed area. In this case here, this also happens to equal the actual area, okay? What I want to do is I want to look at this phrasing here. I want to approximate this with a finite right endpoint Riemann sum. So this is asking you to create a Riemann sum. Once again, what's the Riemann sum? Right here, it's a summation. Approximate this with a finite right endpoint Riemann sum where n equals, let's do 10 subintervals. 10 subintervals, okay? Now I can go ahead and try to draw 10 rectangles in here, but I'd probably get very, very sloppy. But go ahead and let's kind of start with me here. Here I have 10 rectangles. Well, let's see. If 10 is the number of rectangles, that means the width, right, delta x is always going to equal 5 minus -2. So that's 7. All over the number 10. So we get 7/10 is the width of each rectangle, right? Remember up here, everyone, see how I found if I wanted 4 rectangles, I took 2 minus 1 divided by 4. All right, so 7/10 is the width. This is the width of each rectangle. Okay, and in fact, sometimes what's really helpful is you just come inside here and just draw like an arbitrary rectangle, just so you can see it. And we're doing right. I told you to do a right endpoint. So let's call this like first, second, third. Who knows? Like first, second, third. I'll just call this the kth subinterval, just so I can visualize it. That way, k could be 4th, 5th, 6th, 7th, right? 8th, 9th, 10th, first, second, third. And we're doing a right endpoint Riemann sum. That means this is what this rectangle looks like. Right, everyone good? Okay, so this is what this rectangle looks like. I'm trying to get an expression for one rectangle first, and then I can create the sum. So delta x is 7/10, that's the width of each rectangle. I know that the height of the kth rectangle is going to equal the lower limit of integration, or I should say like the left-hand limit of integration, so -2 plus k delta x, right? And the, this here is actually just the kth, so it's f of all of that. That's the height of the kth rectangle. If it was just -2 plus k delta x, that's just the kth right endpoint. So f of the kth right endpoint is the height of each rectangle. The area of the kth rectangle is equal to width times height, correct? So width times height. Oh my gosh, look what I did over here. Delta x times, I just caught this, delta x times. This times became a plus. What happened? Oh my gosh, it's so embarrassing. 1/2 times. So 1/2 times all of this. Oh my goodness. I'm so sorry, but guess what? You know what? These moments make us stronger. 1/2 times all of that. There we go. My bad. Okay. So the area of the kth rectangle is delta x, so 7/10 times f of -2 plus k delta x. But I know that f of -2 plus k delta x, 7/10 times e to the -2 plus k delta x. And I'm going to clean it up even further. I get 7/10 times e to the negative 2 plus 7k over 10. Everyone okay? Everyone okay? That's the area of the kth rectangle. So now my sum of all 10 rectangles, let's go right underneath the picture here, okay? The sum of all 10 rectangles area, of all 10 rectangles areas is going to equal the summation from the first rectangle to the 10th rectangle of, right there, 7/10 times e to the negative 2 plus 7k over 10. Okay, and this is an approximation of the definite integral from negative 2 to 5 of e to the x dx. Okay, so that is it for this screencast. I will say to you this, right? I think it's probably obvious to you that the greater the number n is, so, right? Okay, so as n increases, right, as you increase the number of rectangles, the better the approximation, right? Because the rectangles get skinnier and skinnier and skinnier, the better the approximation. And frankly, I can write this. As n approaches positive infinity, okay, the summation from k equals 1 to n, look at that, okay, of delta x times f of, I'm going to call this, let's say a plus k delta x. Now, when I do this generically, everyone, what does a stand for? Okay, A stands for the lower limit of definite integration. Do you see how I'm just now putting a general, this is just the summation from k equals 1 to n, n being the number of subintervals. Delta x is just generically the width of each rectangle. F of a plus k delta x is the height of the kth rectangle. Width times height equals the area of the rectangle, okay? So as n approaches positive infinity, comma, this Riemann sum approaches what value, everyone? It approaches the actual value of the area, which is the definite integral from a to, what should we call the upper limit of integration? You want us to call it b? Sure. Definite integral from a to b of f of x dx. Okay? So what's really fascinating and sad to me is I can't tell you the number of people who can spew off this relationship right here, but don't know or completely forget what these things mean, right? Like they'll be able to tell me this, and then I'll say, okay, what is f of a plus k delta x? And they'll say, I don't know, it's just in the formula, or it's just in the expression. Well, that's not good enough. A plus k delta x is just the kth right endpoint. F of a plus k delta x is the height of the right of the kth right endpoint, which is the height of the kth rectangle. Why are you multiply times delta x? Well, delta x is the width of each rectangle, okay? So really important idea, incredibly important idea. Please take exceptional notes here. Please annotate where necessary. I used a lot of very specific vocabulary here. Again, I do apologize for my incredibly careless mistake here. I don't know how that happened. Well, sometimes my mouth and my hand just kind of are in disagreement. All right, but very, very important idea. I know you AB students, you know why this is so profoundly important, that you really fundamentally, functionally understand this. This is so important. It is the foundation of all things to come. And with that, I bid you good night.